Well, good afternoon. Hola. Good. It's such a great pleasure to be here in Congreso Futuro, the future of science, technology, and society. It's such an important topic. I do want to congratulate the organizers, particularly former Senator Guido Girard, for organizing this wonderful meeting. It's a great model for this for everywhere in the world. So it's about the future. And I look at so many young people in this room. You're the future. Scientists, citizens, and leaders. And I want to talk to you about the future of medicine. The title of my talk is The Brave New World. I imagine the future in a world where science technology can change and transform the way you practice medicine and healthcare. A future where diseases can be controlled, cured, or prevented. A future where all of us can live well beyond 100 years in good health. I hope so. So I think this is such an important possibility. At the same time, I worry that the future of medicine could face increasing cost of care, skyrocketing, making treatments only available to the rich, but not so much to the poor. I also worry a misuse of technology, the new technology, such as AI and others, which can cause harm to individuals and to society. So I think my main message with all of you is the future is bright if we do the right thing, which is together we have to make sure that the future achieves the benefits of science and tech medicine for all while reducing the risk. Let me start first showing you a set of data. So here we are looking at, in fact, life expectancy, very dramatic. On the vertical axis is years of life expectancy. Horizontal axis is decades, from 1900 all the way to now. Now, it's very obvious to you if you look at this that there's a sharp increase from 1900 to now. In 1900, people lived to about 31 years old. Today, globally, people live to well over 70. And of course, in some societies like yours, even longer. So I think the question really is, how do we get there? Science, technology, public health. It's very clear to me that, in fact, what happened since 100 years ago or less is public health, hygiene, sanitation, nutrition, vaccination, seatbelt, tobacco control. And in medicine, there's tremendous advances in diagnosis and treatment, so that diseases which were death sentences, like HIV, cancer, now are controlled or even cured. Now, so how do we get there? I would say that success will be driven by two scientific revolutions, a biomedical scientific revolution and also a digital revolution. And now the two of them coming together, convergent, and of course in our case, for health and medicine. Now, the biomedical revolution started, I would say, you can say a long time ago. Most of us think about discovery of DNA, right? Watson and Crick, 1950s. But over that time, it's evolved to sequence the human genome, the ability to manipulate genes, and of course, biotechnology and molecular revolution. Digital technology revolution, which I'll talk about later, also started at the same time with the first commercial, huge mainframe computer to now where we are today. Now, I think it's the combination of these revolutions that brings so much promise to the future of health and medicine. So here they are, some of the breakthroughs. I think this has all happened in the last 10, 20 years. Genetic engineering, regenerative medicine, immunotherapy, synthetic biology, precision medicine, microbiome, and of course, also tissue engineering. I'd like to give you a few examples of what is possible today, so you can imagine what will be possible next decade, next 50 years, even next 100 years. So let's take a look at some of these examples. Cancer immunotherapy, cancer therapy. Now, you know that, in fact, in cancer, which I said was a death sentence, it's now possible, of course, to sequence the cancer tissue to find out the mutation and to create precise treatment called precision oncology. And you have come up with cures, many examples. I showed the other side is immunotherapy, where you can use your T cells, engineer this, and then let those cells attack your cancer tissue. Now, you may wonder why I put President Jimmy Carter on this. Well, President Jimmy Carter, the late President Jimmy Carter, had actually metastatic melanoma, skin cancer. He was completely cured by immunotherapy. Allowed him to live much longer, and he just passed away. And what a wonderful leader that we had in our country and globally. In the brain area, the brain-machine interface is restoring function in people with neurological impairment. As you can see in this slide, a paralyzed patient implant electrodes into specific areas of the brain, can send signals to a computer that actually would generate electric command to a robot, where now this lady can function. But you can see on the left side of the picture, the ability of a paralytic, a paraplegic, somebody who has spinal cord injury who cannot walk, being able to walk again because the same idea, brain electrodes in the motor area, drive, in fact, around this injury of the spine to what they call digital bridge. So it allows signals to actually begin to enable a patient to walk. These are all beginning to be possible. And you all know about genome editing, the Nobel Prize. So exciting, the technology of molecular scissor that is being able to use a specific guide RNA to a piece of the DNA and then use an enzyme called endonuclease to cut it specifically. So now you can imagine you can actually take away the disease gene and replace it with a normal healthy gene sequence. So as you can see in the slide, it's now possible to use it for treatment for disease. There are several hundred clinical trials now giving specific, of course, genome editing CRISPR-Cas9 to tissues. In this case, I showed you in terms of a sickle cell patient whose bone marrow stem cell had been manipulated, and now she has cure potentially. And this, of course, is scaling up now to many parts of the world. But I think the real interesting question also for us, and important for today's discussion, is what's shown in the middle. That's possible to take a fertilized human egg or embryo, inject the CRISPR-Cas9 in, and target specific genetic sequences where you can change it, whereby the genetic makeup of that cell or embryo is changed forever. And it will be passed down to babies in generation to generation. So you can see down in this slide is a designer baby, where you can say, I can actually make this person smarter or stronger or even better looking and better vision. And then, of course, in regenerative therapy, we now can regenerate tissues, heart, liver, you name it. And in this case, which I showed you, because I work in this area now, and regenerate the heart, is that human hearts, after myocardial infarction, heart attack, where your blood vessels are occluded, you lose blood flow, and the heart, therefore, cells die. We're not able to regenerate the heart muscles. And instead, we activate cells called fibroblasts to form a scar over. So now you can imagine if you have a big heart attack with a scar tissue and much less muscle, you can go into heart failure and die. So the approaches to regeneration include, of course, injection of stem cells, tissue engineering, and I think very exciting recently, is using molecules to do this, called direct reprogramming. The concept is to say, I can activate the genes in a cell and change it to a different cell by changing genetic material. And this is what I work in my laboratory. We have looked at, is it possible to take a scar cell after heart attack and convert it to a muscle cell, and therefore regenerate the heart muscle altogether. Our approach is you can microRNA, which again this year's Nobel Prize work. But of course what we did, as you can see in the left side of the slide, is a section of in this case a mouse, where you have actually created a heart attack on the top. You can see there's a thin out pieces in blue, which is a scar. But when we introduce the combination microRNA, you can see the heart totally regenerated. And now we have moved into large animals towards human studies altogether. Now, everybody knows about precision health and precision medicine, whereby it's possible to take genomic information and, of course, other information, along with, in fact, a microbiome, electronic health record, lifestyle, you name it, and together you can actually begin to look at data for individuals that can precisely predict and create individualized therapy. Last, healthy longevity. I said earlier, it's possible to live much longer, so it's now possible, as you can see, knowing the pathways for aging, to interrupt the aging process, whereby you can, in vivo, in whole animals and whole in human, delay the onset of aging, resulting free of diseases. And that's already now possible. And many people are now looking towards neuroscience to move into, into treatment. Now, I think what really have to also think about is digital revolution. It showed it started in 1951. Of course, then you have the World Wide Web, and then you have iPhone. Who doesn't have an iPhone? To, of course, AI, and you name it. And in health and medicine, of course, digital revolution was a basis for CT scan, MRI, genome editing, and of course, right now, we talk about how they come together. So you can imagine that with what we can say tomorrow is that AI, digital technology, even though with all the concerns you heard earlier, to me, will definitely change health and medicine. First of all, it can help quickly discover drugs and the development. The AlphaFold, another Nobel-winning discovery, can predict protein structures and make drugs much faster. Of course, as I mentioned already, you can actually have X-rays, CT scan, pathologic imaging, where machine learning can outdo human for accuracy because of the large information they have. Clinical decision support, robotic surgery, telehealth, and of course, operation efficiency. So what would the future look like in healthcare? I would say it will change when it's delivered, where it's delivered, who's delivering it, who's making decisions, and of course, how to improve productivity. All these are now possible, including, as I showed first one, a selfie that you can look at the back of your eye called retina, where you can look at blood vessels, and actually monitor diabetic disease, hypertension disease, and so on and so forth. And of course, AI and avatar, delivering care, robotic surgery, you heard about clinical decision process, data analysis, it's really quite amazing. Here's my question. Mark Zuckerberg and Priscilla Chang initiated a thing called the Chan-Zuckerberg Initiative. In 2016, they put $16 billion down to say, let's advance this technology. Their question is, by the end of the century, 80 years from when they started this, is it possible to manage, prevent, or cure all disease by the end of the century? Can I see a show of hands? Who believe it can be done? Very few. I think it's totally possible. Just remember, 100 years ago, 32 years of life expectancy, no penicillin, no vaccination. I'd say that science technology is now possible to actually do this In 100 years, I've been in medicine for quite a long time. When I started as a cardiologist in heart failure, we have digitalis, which doesn't work. And now there's a school of things, transplantation, so many different technology. So I would vote for yes. But the problem is, would everybody benefit from it, right? So I think the last one of our talk has to do with the fact that the challenges are substantial. If you look at COVID-19, the countries that were poor had no access to vaccine. In the first year, 5% vaccination versus 70% in rich countries. Lots of lives were lost. If you look at gene therapy, costs $1 to $3 million to treat. So many people will not be able to afford this. So I think that's the first question. The second question, of course, is the risk and consequences of innovation. So I'm going to quickly say this slide is my conceptual slide, that in actually moving from discovery research to human outcome, there's two values of death. Most people think about the first value, which is, I have a good discovery, but I need money. I need clinical trial in order to bring it to commercial. I think now, with the kind of things I showed you, that's not so much impossible, but lots of people in the second value of death is called equity. Not enough access, cannot afford it, and we have to overcome this issue. Now, I coined the talk today as Value of Death, A Brave New World. How many people read this book by Huxley, The Brave New World? Okay, quite a few. Huxley, in 1932, 90 years ago, said that by 2540, dystopian world. Imagine that we have genetic modified citizens, intelligence-based social hierarchy, where developments in reproductive biology, technology, sleep learning, psychological manipulation, and classic deconditioning. In 2025, the technology is already there. We have genome editing, we have stem cells, we have AI. So I think the main message is that he envisioned the misuse of this technology to be a dystopian world. We have to be very careful about how we look at this advance in health medicine. So here's some examples. Dolly the sheep, a UK scientist reported this. It's possible to clone mammals. And of course, it's easy to imagine you can clone human beings, right? Genome editing. I talked about the fact you can change your genetic makeup forever by germline. And of course, a Chinese scientist already declared this a few years ago. Dual-use research. You being able to manipulate pathogens, viruses, etc., to make them more pathogenic. Of course, biosecurity. And most recently published only 2-3 weeks ago, this is called mirror life or mirror science. Mirror biology is the ability now to do synthetic biology whereby you can take DNA, RNA, or protein, actually RNA and protein, and to make a mirror copy. They usually are left-handed, RNA and protein, to make a right-handed. Now, you may say, so what? Well, they are biologically active, but they escape the immune detection, and therefore, synthetic biology can be used for bioterrorism and many other things altogether. Of course, you know about AI. You heard a lot about the concern for AI. I too, particularly today in health and medicine, the concern, of course, in fact, inaccuracy, algorithms, biases. But we all know about, data manipulation, blackmailing, hacking, malware, and many others. And of course, the whole list of other possibilities in societal implication, as I wrote in Science in this article, about cost, access, you name it. So let me just end by saying, I think we are now entering a very exciting phase where science is moving so fast. And you can see in this cartoon, I think us little guys are trying to catch up, right? What is the governance? I wrote a paper in the New England Journal of Medicine, and we're working on creating a governance structure over emerging science technology. Before it comes to a human being or the clinical studies, we should be thinking about what's the implication of this technology? What is the potential side effect? And begin to mitigate this rather than just put it into the market, and then try to catch up with problems. So, a brave new world. I'm going to end. I think we, scientists, clinicians, civil society, political policymakers, and everyone should come together to say, if we want to achieve the potential of new technology, we must have robust oversight. And we must have the principles of equity, fairness, and justice. We must be trustworthy and transparent, and of course we have a responsibility, which means all of us have to come together, have an ethical responsibility to consider the social implications of these advances. So I would say it's very exciting, the future. Medical technology breakthrough advances, I believe, will transform medicine. I believe that in 80 years, it's possible, in fact, to address all the things we have, even though new diseases, because our technology is going to be there. I think the question for all of us is to be sure that we use these technologies appropriately. Thank you very much.